Okay, so here's part two. So we've got our expression for C. We've related that to CTV because it's the speed of light by the time taken. And we know that that's equal to this distance here. And we've got an expression for the distance here, which is 2 lots of the hypotenuse. So now we're just going to equate the two now. We've got CTV equals square root of, and all I've done here is just put the 2 inside the square root sign. So if we square the 2 and put it in, it becomes 4, okay? We put the 2 in here as well, and we'll find that the 2's, because that's 2 squared on the bottom, that's a 4. I put a 4 out the front here, they'll cancel out as well. Okay, so you can see I've actually applied the square to the brackets here. Okay, so I end up with this expression for CTV. Okay, so I've got this expression here, which you can check. Now what I'll do is I'll square both sides, and as I square both sides, you'll see that expression opens up into these terms. And you'll notice here what I'm going to do is I'm just going to grab the v term for v squared and bring that over to the left-hand side. So because it's plus, when it comes over, it becomes minus. Okay? You'll see here I've got now c squared tv squared minus v squared tv squared is equal to 4l squared. And what I'm going to do now is pull out a common factor of tv squared, okay, which is equal to 4l squared. And then I'm just going to leave the tv squared on one side and bring my c squared minus v squared and drop that to the bottom here. Sorry about the background there. Okay, so now that I've done that, let's have a look and see what happens. I'm going to actually square root everything. Okay, and when I square root everything, the TV, the time in the moving frame, comes out to be 2L on c squared minus 4 squared. Now, some of the mathematicians may say, oh, we're a little bit stuck here. There's a little trick that some of the 3-unit and 4-unit guys might know about. So what I'm going to do here is I'm actually going to pull a factor out of c squared minus v squared. But the way I'm going to pull the factor out, you'll see below here, is I'm going to pull c squared out of this. And what I do is I just invent the c squared in the bottom here. So when I put the c squared back in, they'll just cancel out and leave the v squared there. Okay, so if you have a look now, I've got 2l on square root of c squared outside of 1 minus v squared on c squared. And you'll notice now that if I take the square root of both individually, that what I get is 2l on c outside of 1 minus v squared on c squared. Okay, so this c, if you like, when I square root it, just becomes c, and I've got this equation. Now here we are here. I've got an expression for TV in terms of 2l on c, and I've got the square root of 1 minus v squared on c squared. Now, some of you may go, oh, 2l on c, I think I remember that. Well, you remember earlier on, we actually determined an expression for TO. And we determined this expression for TO as being 2l on c. Hang on a minute. Now I've got a way to relate TO, that is the time in the rest frame, to TV, which is the time in the moving frame. So here we go. Let's substitute in now for 2l on c. So what I'll do is, just to make this look a little bit nicer, is I'll bring the 2l on c. I'll separate that out. Just split the expression up into two terms. And so 2l on c now, we know that that's TO. So I can just put TO out the front here. And when I multiply these two together, I end up with this expression. The c squared on the bottom there is just a little bit taken out. Now, what you'll notice is when you look at the equations on your formula sheet, TV is not written as TV, it's written as T, okay? But the TO is still notated as TO, being the time in the rest frame, and T is the time in the moving frame. So you'll see now, here are the all the variables and what they are. And then you'll notice there's something that happens here which we need to talk about. We need to talk about this. This is called the Lorentz factor. Okay, and this can sometimes, in your book, you'll see that's represented by gamma, okay, which is fine. But I think the thing to notice and really look at is this v squared on c squared. So we need to know that under the square root sign, you need a positive value, which means that v squared on c squared can never be greater than 1. Okay, so this is interesting. If v squared on c squared is always less than 1, that means that v squared must always be less than c squared. So this means that in terms of the train moving, the train can approach the speed of light, but it means that the train can never travel at or greater than the speed of light. Okay, and we'll discuss this later in class. So a simple way to think about this is that I've written here moving clocks run slower. When you start to actually put some numbers in for different relativistic speeds, you find that the time as observed from the external observer is different to the time as observed from the observer in the rest frame. So moving clocks run slower. That is, if you're in the external frame of reference, you'll see time dilate because it takes longer for that um, ray from that light to go from the top of the train down to the bottom and back again. So if we just go back to the pictures and have a look, okay, so this one down, straight back, this will take a little bit longer to get back, okay? So I think I'll stop there.